Hey everyone, welcome to the session by Intellipaat. My name is Anirudh and I welcome you all to this session on convolutional neural networks. Well guys, before we begin with this session, I hope you guys are all safe in quarantine, following all the safety procedures and keeping your learning up at the same time. On that note, I welcome you to this session, and before we begin, make sure you subscribe to the Intellipaat's YouTube channel and hit that bell icon so that you never miss an update from us. Alright, let's check out the agenda for this session. We'll begin by quickly taking an introduction to convolutional neural networks. After that, we'll check out the need for convolutional neural networks in today's world, and after understanding the need, we can go on to check out the overview of all of the neural network concepts that we'll actually need for convolutional neural networks, and we'll check out the detailed working, every single aspect there is to know about convolutional neural networks in a very simple way. And at the end of it, we'll have a demo by making use of convolutional neural networks with Python. And last but not the least, I'll be guiding you guys on how you can become AI experts and deep learning experts in the easiest way possible. Well, this brings us to the first item on the agenda. So here are some of the things that I would like to ask you guys. As always, let's keep this session very interactive. So head to the comment section below and do post all of your comments. Our team is standing by and will be more than happy to help you out. Okay, here is the first thing. Do you know how these work? For example, here is Facebook. Guys, I'm sure most of us use Facebook, right? So there's pretty much, 90 or 95% of our viewers actually use Facebook. So when you think about it, think about the situation. Let's say you and your friends went on a road trip or a small tour or something, and then what happens is you click a lot of pictures, 25 pictures, 30 pictures, and probably 20-30 selfies as well. So when you do all of this and you upload it to Facebook, so here if you have to tell your friends that you've uploaded a picture, you do something called as tagging, right? Photo tagging. So basically with respect to Facebook, now there is a very intelligent feature which is something like it is auto tagging people for you. So instead of you manually picking up the person's face 30 different times for 30 different pictures, Facebook will now recognize that person in all of the 30 pictures and pretty much go on to put their faces there directly as well. So the question here is, how does Facebook know what person is in the picture, and how does it even recognize the face for that matter, and much more, right? So this is one of the things. Think about it. The second thing, when you go to Amazon or any other e-commerce site, most of them do it now, but then Amazon do it really well. So when you buy something, or when you buy, let's say a couple of books or something, and you add certain books to your cart or whatever it is, after buying it, or when you're scrolling around on Amazon, you will see something like recommendations for you. Well, how does Amazon know what to recommend for you? I mean, of course, you might have bought a couple of computer or related books, or for example any Google related books like it's shown in the example out here. So Amazon will basically go on to give you an even more insight. It will basically have all your search results, all the items that has been added to your cart, and of course everything that pretty much you bought through Amazon as well. So it uses all of these, and there is some intelligence in the background that's going on to basically recommend all of these books for you. Do you guys know what it's called? Well, of course, it's called as a recommendation system, guys. But the first thing, it's image recognition. With respect to Facebook, with Amazon, it's recommendation systems. Now let me come to Instagram. Instagram is something, again, another amazing social media platform that pretty much most of us use as well. So when we're talking about Instagram, these days you'll see a lot of advertisements there which are actually customized for you. So let's say you're on Google, searching for, let's say, the top car of 2020 in India or in US or whatever it is. So as soon as you open up the Instagram app later, and once you're browsing, the ads are so subtly put together that in the advertisements you will see cars, car parts, and you'll see like some trending car brand which is basically on the top, the most sold car and all of that. So how does Instagram's advertisements get to know that you were browsing for cars, and now these advertisements are basically helping you to find those cars? See, relatively or non-relatively, you might click or might not click on that particular advertisement which is being shown there, but at the end of the day, pretty much you will know that that is something that you would want to see. This is what Instagram wants you to understand. All right. So coming to the problem, coming to the actual concept of, where CNNs are used, why CNNs are used, to understand all of that, we need to understand the problem, because neural networks, especially convolutional neural network, was a solution to a problem. To understand what they are, first let's check out what the problem was. Coming to the problem, it was image classification. See, basically what image classification actually means is, so basically, when you're shown 4 or 5 images, you will have to classify it and categorize it into one or more types. For example, if you've shown 3 black and white images and 3 color photos, you have to, and all of these are jumbled up. You as a human being, you're trained to pretty much, separate all the black and white, separate all the colors. Now, it's not this simple when it comes to making your computer do this. See, as human beings, we are sentient. We can think, and we can think in a very rapid way. We have like millions of neurons in our brains firing and helping us understand everything that goes on around us, right? But then with respect to computer, basically it's silicon chips with programming which works on high level programming languages and low levels such as binary zeros and ones and whatnot. So to make your computer understand images, to make your computer help you classify the images and more, we needed something. We needed a solution, and the solution was convolutional neural networks. See, for example, you can input a lot of images to your machine and get your machine to output a class. For example, there's lots of pictures of cats and lots of pictures of dogs, and then your computer can be trained. It can be taught where it'll pretty much understand what a cat looks like, what a dog looks like, and then it'll tell you what the cat is, which image was a dog, and much more. So this basically the task of image classification. It comes very easy to us as humans because we have been trained since birth. So think about it like this. So when you were a kid, when you were an infant, pretty much, you would have been shown what a dog was, what a cat was, or you would have seen it in the books that you were studying, and your parents would have, had pets, and you would have understood what a cat looks like, what a dog looks like, and whatnot. So your brain has been trained over the years to understand, what these images are, what it looks like, and what they are. But then when it comes to computers, the computers basically, they do not understand this. So you have to train them. This brings us to the solution. You, as soon as you see this image as a programmer, as a developer, you can say, hey, those are the 4 probably the cutest dogs that I've seen online, right? So of course, as soon as you see this, you get this. Now, what does the computer see when you have to work towards the solution? When using convolutional neural networks, or basically when deciphering any image, the computer will see something like this. You are seeing this beautiful image of dogs while your computer is seeing a matrix. A matrix is basically, a data type which has multiple rows and columns, where each row of each column will have a value filled, as you can see on your screen. So look at the sheer difference between what the computer sees and thinks versus what the human sees and thinks, right? So this should give you more clarity about making your computer go from all of these numbers to help it understand that this is a picture of the dog. That's the goal here. All right. Now, if we have to do something to solve this problem, so we know the problem, we know that the solution is obtained through convolutional neural networks. So what are some of the image inputs and the outputs? What does it look like? What does the inputs look like? What does the output look like? And much more. And that's exactly what we'll check out now. See, coming to the input and the output, I'll give you another example. Check this out. This is Mozilla Firefox's logo. This is an amazing browser in my opinion, and this is what an image looks like, right? So it's a general image. Now, this is what the computer can make sense of it. See, for example, for the people who are not getting the difference between the 2 images, the second image is actually blown up. It's a little bit compressed, and you can see every single pixel that goes on to make the Firefox logo. So basically, when you keep zooming into these logos or any image for that example, it starts pixelating. So pixels are the individual entities that actually go on to make an image. You'll have thousands and thousands of pixels which will basically, make one single image, and each of these pixels will have a specific color to them. So when you zoomed in, you can look at all the individual colors. See, for example, you can see all the yellows here. There's shades of oranges, and there's dark blue, there's a lighter blue, and it gets lighter as soon as you keep coming in. Now look at this here. You cannot see all of those pixels, but then you can see how those pixels are blended enough to give you this beautiful looking image, correct? So when it comes to working with pixels like these pixels, you need to understand one important thing when you're working with pixels. It's that, let's say this is an image which is basically 32 cross 32 in its image resolution. So by image resolution, what we basically mean is that there are 32 pixels in its width, 32 pixels in its height. And with RGB, the color scheme that we follow to basically use and work with color images, of course, there are other color schemes as well. There is CMYK and there are many others. Here, let us consider the RGB model. So when you're working with RGB model, what usually happens is, so basically to achieve all of these colors, they are the mixture of three primary colors. If you want a different color, you will mix red and green. If you want another color, you will mix green and blue, blue and red. So all of these combinations will basically give you a new color. That is how we see millions of colors. It's not like these colors are independently existing on their own. So coming back to the example where we have 32 pixels of height and 32 pixels of width, what we're actually trying to mean is that each of these pixels are followed by three things. Three things are basically these three colors which are followed in each pixel. Alright, so let me repeat that again. So when you're talking about an image where each of the pixels are being considered, each pixel, if it's a color image, will have something called as three channels, and each of these channels are basically one being red, the other being green, and the third one being blue. Hence the cross 3 at the end, 32 cross 32, height and width, and into 3 because that is the total number of pixels that are present in the image. Now, to further elaborate on this, here is a beautiful look at a sunset. So as you can see, the width of the image is 1080 pixels. Pretty much the length of the picture is 1920 pixels. So the image definition becomes 1920 cross 1080 pixels, right? Now, the number of pixels there, the number of RGB channels that are present is 1920 into 1080 multiplied by 3 because there are 3 channels, one for the red, one for the green, and one for the blue. I hope I was very clear with respect to making you understand what this means. And of course, let's come back to the same image again where we have to discuss one more tiny concept when you're working with pixels. So it's not just the presence of the color that we deal with all the time. It's the brightness of the colors. Let me point it out very subtly. For example, if you look at this part of the sky, this looks a little bit bright. It's a brightish yellow. And then when you look at a point like this, it's orange, but there is some yellow in it, but it's not as bright as what you see. For example, look at the cloud. The clouds are darker compared to the sun rays that we can see there, right? So what am I talking about? I'm talking about the brightness. So when you're working with any image, it's not only the placement of the pixels or to tell you what pixel is turned on, what channel is turned on. For example, if red is turned on, the entire image is red. Green is turned on, the entire image is green. So to control the brightness, each of these pixels will basically have a value ranging from 0 to 255. If it's 0, it means that particular pixel is off, and this creates a color called as black because nothing is turned on. There's no light which is present there. And as soon as the value starts climbing up from 0 all the way to 255, the brightness of that particular color channel will keep going up. And that's how brightness is managed alongside the three color schemes when working with all of these images. Now, after understanding that, we need to come check out something called as a human connection. What do I mean by human connection? Well, it's pretty simple, guys. See, we can see all of these images around us and we can understand something that we see because of this particular entity in the human brain. It's called as the visual cortex. The visual cortex is a very important aspect of the human brain which is responsible for a plethora of tasks. Now, how does the brain assume or see something in 3 dimensions? Of course, I am giving you a very, very simple overlook to make sure that you basically just get the concepts of what goes on. For example, since we are on YouTube, I just picked up this YouTube logo. It's basically a 3D emblem kind of a thing of the YouTube button. And as you can see, it looks like it's pretty much, popping out of your screen. And as soon as you look at it, most of us can take a guess that it is a YouTube logo, right? Now, how do you make sure that a computer sees this and it understands that it is a YouTube logo? Well, there are 2 important things when it comes to helping your computer understand images. It's edges and corners. When it comes to working with edges and working with corners, your computer can be programmed to understand an image by going through each of the pixels there, by understanding what is present, what is not present, and at the end of the day, it will create matrices in the back end. So, it has an understanding of its own of what these images looks like when it's brought down to its most simple entity. For us, the most simple entity can be pixels, but for the computers, they can go and simplify it even to another level where it basically becomes numbers. Again, I hope I was clear with this concept as well. And now, coming to the computers. Well, what happens in a computer? Let me tell you this with this beautiful visualization here. There are pictures, let's say, there are dogs and cats on the image which basically you want to teach your computer about. Now, when you look at the commonalities present between a dog and a cat to help it understand, both the dog has a tail, the cat has a tail. For example, the dog has 4 legs and the cat has 4 legs as well. You can pretty much get the paw print of a cat and a dog to find some differences between what a cat would look like, what a dog would look like, and much more. So this basically will be a combination alongside something called as a labeled data set. A labeled data set is basically images of, let me give you an example. It's basically images of, let's say, cats and dogs, where basically the images are already labeled as cats and dogs. So once your computer sees all of this, it'll actually know what's a cat and what's a dog. Now it has to learn to pretty much get back to the result. It'll have the data, it'll have the result. Now it has to give you the method through which the result can be obtained. That is all about image recognition, guys. So basically it will be fed labeled inputs into the computer. You will be programming the computer by making use of various deep learning frameworks out there, and at the end of it, it'll give you a positive rate saying, hey, this picture is a dog or this picture is a cat, and what is the probability that the picture is a cat or a dog, and much more. Guys, this is a very simple example to make sure that the concepts are being understood by a wide variety of audience we have here tonight. Alright, now let's quickly move to the introduction of convolutional neural networks. So guys, from this slide on, make sure you pay a lot of attention to understand all of the concepts that are being taught. And as always, if you do have a pen and paper available, make sure you bring it towards you so that you can check out all of these concepts and take notes alongside if you want. Now, coming to the convolutional neural networks. So when we talk about convolutional neural networks, or CNN as it's called in short, there are 3 important steps which happens to basically help in image recognition. CNN is a very widely used type of neural network which is used for image recognition, as I just mentioned. Now, with respect to what neural networks actually are, neural networks are basically implementation of programming and implementation of mathematics to help computers try to recreate what happens in the human brain. Hence it's called as neural network. Neural basically refers to the neurons present in the human brain, and the concepts of working of a neural networks are fabulous in my opinion. We do have in-depth tutorials on the channels for neural networks in general, so make sure you check that out after this session as well. Now, coming back to the 3 important steps of what makes a convolutional neural network what it is. First step involves something called as the convolution, and then we have something called as the activation function. After the activation function has been performed and has been worked on, then we have something called as the pooling layers. Well, if you know what all of these means, again head to the comment section, do let us know what you think about each of these layers. And of course, if you do not have an idea of what these means, do not worry, I'll be covering all 3 of these concepts in the coming slides. So this quickly brings us to convolution. What do we mean by convolution? Well, the convolution operation, what we talk about, is basically one of the most foundational concepts, as you probably would have guessed because of the name. Pretty much what it tends to mean is that, it will basically help your computer understand your image better by being the foundational step where your image can actually be understood by the machine that you're working with. So here I just picked out the logos of the top social media platforms out there. This can be any image you want. It can be image of a cat, it can be a photo of you, it can be picture of a landscape. You get it. So basically, when this image is considered as the input image which you're giving to the machine, let me repeat that. When this is considered as the input image, which is basically what you're giving to the computer to learn, it will know what it is because of the labeled data. It knows the input image, it already knows the result. Now your machine will tell you how to get to it. So to make your machine understand this image, there is something called as a filter that is basically put when you're working in the convolutional layer. So when you're talking about it, let's check out this particular matrix that I have. Think of this as an image which has been broken down into the pixel level. Now, when you're looking at this 6 cross 6 matrix, basically, to put it in very simple terms, wherever you see zeros, consider that that part of the image is dark or the pixels there are off. Whenever you see a number which is greater than 0, it means that the pixels there are basically turned on, and you can put in a visual representation where these, wherever the first 3 columns says 10, you can draw a line of adding 3 pixels and then everything else is 0, which basically means they are dark as well. So when you're working with convolution, the filter aspect comes into picture here. Filters are again an amazing entity, and when you're working with convolutional neural networks, they are a lifesaver. Why do I say this? Well, let me tell you this. Now, when you're working with the convolutional neural network and especially the convolutional layer, you will have to take the input image and put a filter across the input image to basically let it understand that that there is something here which is basically a matrix of, let's say, RGB values, and the process basically involves superimposing or putting the filter across each of these elements in the convolutional table, and which makes and at the end of the day, it basically adds all the values from the filter, it adds all the values from the image, and it will generate another different layer for us. So this layer, which is basically the product, that is called as the convolutional layer. So let me repeat, how do we go from the input image to a convoluted layer? Well, an input image is taken and an entity called as a filter is applied to this convolutional layer. So upon performing an operation which is basically called as a dot product, we basically arrive at this final product which is called as the convoluted layer. Well, it is actually a little bit tough to tell you this with respect to words. So let's go on to visualize what it would look like. So even before we look at the convolution, let's quickly take a step back and look at what the pixels depth would look like when you're working with edges and corners, as I mentioned. So here is a silhouette image of the background image of particularly a lion, and as you can see, when you've picked up a small tiny field of it, this is what it would look like. So everywhere where there is zeros, there are no pixels, so it means it's all white. Now as soon as you start seeing the grayscale images, as soon as the numbers go up, you can see the darkness of that box is going up. So this is how the pixels work when you generally look at an image. So the darker the box, which basically means higher the number literally means that there is more content around that. Now if you can look at the center line of this aspect, it is the darkest. As soon as you keep going towards the corner, it gets lighter and lighter, and eventually it wears off into the environment, right? Now this is exactly what you can see. As you can see, 252, 198, 220, 168, all of these can be considered as the innermost aspects of it, but then when you start looking at the outer borders of it, the numbers are really less. So this is basically a matrix of what would an image look like for a computer. So now let's quickly get back to convolution and visualizing that. As we talked about an input image being a matrix and applying a filter on it, now here is what an input would look like, and here is how the corresponding output would look like when we perform a dot operation between them. See, for example, as you can see, our filter is 3 cross 3, 3 columns and 3 rows. So basically when you go on to put this filter on your input image, all we're trying to do is we actually run the filter across each of these blocks here. And when you're running across each of these blocks, whenever you go across one single block, it will actually give you one number, because you're summing up all the numbers that are present there with respect to the product of the filter and that particular entity. So let me repeat. So when you're running your filter across your input image to basically superimpose it, what we are actually doing is, so basically we're trying to get out one single feature map out of the huge data that's present in the input. So performing an activity such as this will look something similar to this. So for example, we have let's say this is our filter. It's 1 0 minus 1, and the same for the other rows as well. Now when you go on to take this filter and basically superimpose it over here, what actually happens is that there is a dot operation. For example, here is what the output would look like, and as I mentioned, when there are zeros, there is no pixels lit up there. When there is a positive number, there are pixels which are lit up there. So how do we go from these two matrices, one being our input image image, one being our filter, to basically this resultant matrix. So let me give you one example where you will understand this very easily. Now let's consider that we're taking the filter and running it across the first three rows and columns of our matrix. So this basically we're arriving at a number 0 here because we do an operation when you're working with a dot operation. It says that we take all the first columns of the first matrix and multiply it with the first rows of the second matrix, and then we take the second column and the first row, third column and the first row, and this operation goes on. Second, it goes on to, so basically second column and the first row, second column and the second row, second column and the third row, and eventually when you're multiplying each of these entity, the results are getting added to each of the numbers. So basically when we run it across the first three cells, what will happen is 10 into multiplied with 1 becomes 10 plus again another 10 multiplied with another 1 will make it another 10. This 10 multiplied with this 1 will again make it another 10. So until now we have something, we have a number which is basically 30. And then if you're coming to the next row, 10 into 0 is basically 0, 10 into 0 is again 0, 10 into 0 again is the third case, which is again 0 as well. So when you're adding 30 with 0 for this particular case, it's going to be 30 itself. Now, but then we have a 0 here, we don't have a 30. Why? Because we have another row and a column we need to work with, ladies and gentlemen. So basically 10 into minus 1 is minus 10. 10 into minus 1 again makes it another minus 10. Finally 10 into minus 1 makes it another minus 10. So adding all of these minus 10s, we get minus 30. So we have a plus 30 from here, plus 0 from here, and minus 30 from here. So what does that give us? 30 plus 0 minus 30 is pretty much 0 again. So this is the reason we have the 0 here. So basically we are arriving at this 30 because we're moving the feature map right towards the input image as well. So when you're superimposing these operations, as I gave you one single example, by following this same animation that you can see on your screen, when that entirety of the operation is performed, you will arrive at this goal, which is basically this particular matrix. And this matrix will the output is basically called as the output feature map. And you will understand more about this in the coming slides. Now your question might be, okay, we have something called as the convoluted layer where you're supplying the input and we're giving it a filter so that it can understand the image, and you just randomly picked out 1 0 minus 1 and all of these numbers here on the filter matrix, right? So your question might be, wait, okay, I understand this part of it where it's light and dark pixels. So how can we go on to analyze and understand how to pick the right filter to make your computer understand it better? Well, this question is of course natural, and I'm sure most of you might have already asked this question in the comment section saying what is the right filter to pick. Let me begin by telling you that there are infinite values that you can put in your filter to see if it works or not. Because what's amazing about filters is that these numbers that we put in for the filters, each of these can be an output which is based on something which is already trained. So what I'm trying to tell you here is that all of these elements in the matrix can actually be parameters which can be trained enough to see what is the requirement for your particular model. In one case, you might be trying to find out what a cat looks like. In another image, you might be finding out what an aeroplane looks like or what a boat looks like. So if you keep the same filter for all of these, your computer will have a hard time, running through these images, superimposing them, and understanding what the images actually are. And this is why there is the infinite value, as I just mentioned. So what basically you can do at this particular point of time is to make sure that you can choose a filter which will basically work for you and it has worked for your previous application. So if you have had and created a dog or a cat image classifier, you will have a particular filter there which would have given you a lot of accuracy in detection. You can go on to use that, or there is a concept called as back propagation when you're working with neural networks as well. And this is the second way on how you can choose your right filter. So basically when you use back propagation to talk to the previous layers in the neural network, we go from the inputs to the outputs. So when you do this, the back propagation will basically help the previous node correct some values, make changes to certain values to ensure that it keeps a track of what it's learning at that particular hidden level. So with respect to using back propagation, propagation, you can actually find out what values will work, what values will not work, and then create a filter and then use this filter for your input image for the superimposition activity that goes on in the convoluted layer. I hope again that I was pretty much clear to this, and by making use of either of these, you can actually train the values by making use of modeling, or by using backpropagation, you can arrive at the right filter. Again guys, if you want to figure out the entire working of neural networks in a very simple way, we do have videos on the channel, so make sure you check that out. So at this point of time, you would not require the entire detailed working of neural network, as again I'll be covering this in our demo session as well, so make sure you stick till the end for the demo. And now coming to the second aspect of convolutional layer is basically something called as padding. So when we have to talk about padding, let me give you this example again. We'll take the same filter up, we'll take the same input image, and we'll take the same output filter map. So this is a 6x6 matrix, which is our input image. 3x3 is the filter we superimposed upon this to get a 4x4 matrix as the output. So what basically happens is that with every single time we do a convolution over an aspect of an image, the input basically shrinks, as you can see on your screen. So our input was a 6x6, but after doing the operation, our output is now basically a 4x4. Now there is only a certain level to which you can shrink it, right? See, for example, I have pictures of a t-shirt here. So you can go on to shrink it to a level where it will actually, not be usable at all. I mean, I'm not talking practically, but then just look at your screen. The first one is a very clear looking t-shirt. The second one looks okay. The third one, you can find out if it's a t-shirt or not. The fourth one is, it's almost that you cannot figure it out that it's a t-shirt. And as smaller as it gets, it makes it harder and harder even as a human to understand. Now this for a computer is again another issue where even it cannot understand what it's being looked at, because since I showed you that lion example, you could able to figure out how these pixels are associated with the corners and the edges, right? Now whenever there is a pixel which is basically in the corner of the images, so these are only used once. Now if you go on to keep shrinking these images, this is going to create a problem, because at the end of it we will not have another image to work with. For example, if this 4x4 is the output of the first convolutional layer, so then we can put another filter across this particular layer and shrink this matrix even further. So with this shrinkage, there is a huge problem, as I just mentioned. And now with respect to padding, there is actually a fix for this. So as you can see, here is another sample input image for you guys. So whenever I say an input image, think of the matrix, all right? Now this input image is what it was basically a 4x4 as the original image. Now we have added a padding of zeros across this in the borders of it, basically to ensure that we get the same size as the input. See, for example, so in this particular case, padding is 1 because we have added only one row of zeros and one rows of columns to the borders to make the image again become in a bigger size. Adding these zeros will absolutely not affect the image in any way, because zeros again there is nothing there, the pixels are turned off there. This is to ensure to maintain the size criteria which is basically used to calculate the output, and this makes it very effective, and this makes it so important, especially not to lose information when you're working in the convoluted layer. As I just mentioned, with respect to shrinkage, you will be losing a lot of information. With respect to padding, we can bring it up. With respect to padding, we can bring the size up to ensure that there is nothing missing there. So how do you know what padding to apply, and how is this padding even calculated? Well, here is a very simple example followed by the equations that I'll give you on how you can achieve here. For example, as our input image was a 6x6, we're going to be applying a padding of 1. If you're not clear about this, do not worry. Right now, you're going to get complete clarity on that. Now, so the obtained image at the end of the day, after you have added some padding to it, is an 8x8. Now, when you apply a filter of 3x3 and you remember the superimposition animation and the dot product operation we did, now once you go on to do this, basically your 8x8 input will actually become a 6x6. Now there is one important aspect that you have to look at it here. Now the input size and the output size remain the same. The output size is not less than the input size as we checked out in the previous example, and this is exactly why we need padding. Now, when you talk about the equation that actually goes on to calculate padding, in fact, here is the exact equation. So it's n plus 2p minus f plus 1. N is the input shape, p is the padding shape, and basically f is the actual filter shape. Now when you're working with the input shape, as you can see from the screen, it is 6. So n becomes 6. Your padding size, we're going to pad it with respect to 1. So padding becomes 1. So 2 into 1 is 1 again, minus f. F is the size of the filter, as you can see from here. The filter is 3. So as soon as you put 3 here at the end of it, you will get, as soon as you solve the equation, that is, you will basically get the output size. You have to give the input size, the padding size that you want to give, and the filter that you're applying on that particular input. And at the end of the day, it will tell you that for your input with respect to this much padding and this filter shape, your output will be 6. In our case, it was 6. For example, you can pick up another different example. For example, n can be 7. You can have a padding of 1. The filter can still be a 3 cross 3, and you can add 1 as per the equation, and you can get to know the output size for that particular input as well. So guys, this equation will hold true if your padding is 1. If your padding is actually 2 or more, the equation changes slightly by this concept what we call as stride. Stride is basically the number of padding slots that you'll be applying row wise and column wise. So the formula changes into actually n plus 2p minus f divided by the stride. This is one operation, and after that we add the 1 at the end to it. So the derivation of the equation, or for example the concept of padding being more than 1, in my opinion might be too much for you guys to take in at this point of time. So I have just taken that apart, and I thought it deserves a mention. So of course I'm telling you what it means. Now the second reason is that, so again reiterating on the primary usage of the padding equation, the second reason, apart from keeping the input size and the output size to be the same, it is basically us trying to create a convolution where the image size is the same, the input image and the output image, and to understand what values that we can put to come at this solution, guys. So I hope the padding equation was very clear to you. To reiterate it, basically we took the input image, we ran a filter across each of the elements there, we did the dot product of it, and we had an output filter. We realized that the output filter was continuously shrinking in size, and to make sure that we do not let this image shrink and be unusable, we basically add something called as padding. We saw how to add the padding, and eventually we took up the equation where the stride is 1, and we checked out how the output size can be obtained for that particular input, for that particular filter, and the respective padding as well. Alright, now this brings us to the next concept, which is basically the activation functions. So what are activation functions? Let me give you an example to basically walk you through what they mean. So here on your screen, you can see something called as the ReLU. ReLU is basically nothing but the rectified linear unit. It is a type of an equation where you give it a sort of an input and you get the corresponding output to it as well. In this particular case, what can you see on your screen? Of course, I'm going to explain that in a second. But then you can see that all the negative aspects of whenever you input something, it remains 0. But then once the equation starts seeing the positive numbers, the output will actually be exactly that. See, for example, x can be anything in this particular case. If x is minus 10, the output is 0. If x is minus 300, minus 0.1, minus 0.01, whatever it is, if it's a negative number, all these are filtered out to be zeros. And then now, if you're considering positive numbers, if x is 1, yes, it comes out as it is, y is 1. If x is 2, y is 2, x is 3, y is 3. So as you can see, especially with respect to the negative inputs, the output is always 0. Regardless of the number, if your input is negative, it means that the output is 0. And then when you look at positive numbers, whatever it is, it comes out as it is, because y is basically equal to x. Whatever x value you provide, y value comes out as it is. Now, why would we need something like this? Why are we filtering out these negative numbers when we're using activation functions? Well, when you're looking at understanding how the neural network works, especially the architecture of a neural network, so these activation functions are basically the mathematical equation which works in the back end of your neural network to help you determine what is the correct output that has to be obtained at each particular stage. If you can see the diagram of a neural network, you'll understand there are multiple nodes there, or neurons as we call it. Now, if this neuron, to understand if the neuron has worked to give you an output or what neuron has not worked to give you an output, this basically is figured out by making use of something called as the activation function, guys. So this is directly relevant of how the model works and what the output is, because as I just mentioned, to find out what neuron was activated, to find out what neuron works and what doesn't work, we need something called as the activation function. And ReLU, or the rectified linear unit, is just one simple example that I brought out to explain this concept for you guys. Now, what is the need for activation function if I have to reiterate on it with respect to what we are working with? So with respect to the neural network aspect of it, I gave you the reasons. Now here is why the activation function is very much necessary when we are working with images especially. So the filter image that we actually go on to supply to our input image to superimpose it is actually very sensitive. It is very susceptible to a lot of noise, and it is susceptible to a lot of deviation. As I just said, your filter cannot be set and forgotten in a way where you can use the same filter over and over again. That doesn't work. Well, if that doesn't work, what else can we do? We make use of this activation function to ensure that your model does not filter through all of the noise. Your model does not become inaccurate because it is seeing a lot of noise in your data, or it is being confused by a lot of deviation around it. To make sure all of this applies, we use the activation function. I hope this was clear to you guys. Now, after the convolution happens, and after we go on to perform padding on that, and after we set an activation function for it, the next important concept is something called as pooling. Well, what do we mean by pooling, and why do we require pooling is the question that you guys will be having. Well, let me tell you this. Whenever you're looking at any neural network model, or whenever you're basically understanding what these convolutional neural networks mean, the first thing, as we already discussed, were the three important steps. After understanding these three important steps, we pretty much came on to checking the first two steps, and we arrived at this particular concept of pooling. For all the ladies and gentlemen who have joined right now, we just finished working with the convolution layer, we understood padding, and we've come to the pooling layer now as well. So basically, with respect to pooling is another method, it is another way to basically go on to reduce the size of the image. So wait, now you might be thinking, all this while we were making use of padding and whatnot to increase the size of our particular input matrix, and now we want to reduce it. Why do we want to reduce it? Well, we want to reduce it because even though your image might be smaller and you cannot comprehend it, your machine can. Making your image size smaller will speed up computation, because your computer will not have to work on so many pixels when it can probably understand it in a small number of pixels, and it will make sure that whatever feature that is basically being detected there, if it's an edge, if it's a corner, if it's something shiny, if it looks like a wheel, if it looks like a rectangle, or whatever it has detected, it will add a lot of robustness to all of these features when detected. So to reiterate, pooling is basically one of the other methods used to reduce the size of your image. We do this image reduction in the pooling layer to basically help your computer actually go on to speed up the computation. Now at the first layer convolution, again I'm repeating, we're going to keep the output size to be the same as the input size after working on the pixel, to make sure we don't shrink it to an unusable level. And now with respect to the pooling level, after the activation function has been performed, you can actually go on to reduce the size, where with respect to what the activation function's output is, your computer would have already understood what that particular image means. So you can go on to reduce the size of it and basically help increase computation to a very high level. Now, to give you a better understanding, to give you a better idea of it, now let's quickly go on to visualize what this would look like. So our goal here is to basically reduce the size of the image, right? So to reduce the size of that particular image, we need a method to do it. There are multiple types of pooling which is done. We have average pooling, we have max pooling, and many other types. So in this particular case, let me explain what max pooling is to you, because this is one of the most widely used methodologies of pooling in the pooling layers. So here I've color coded these particular aspects of the input matrix out here, right? So with respect to max pooling, what you can check is that let's consider the blue aspect of it. Here we can condense these four inputs into one single input just by picking up the maximum element there. As you can see, 0, 1, 4, 5. What's the maximum element here? It's 5. So we club all of these and we just pick up the maximum from there. 2, 3, 6, 7. What's the maximum? It's 7. So 7 gets picked out. And then 8, 9, 6, 5. What's the maximum? 9 is the maximum from the orange. So we pick out this entity as a result of the max pooling. And again, similar case, guys. What is it for the green one? It's 3, 4, 7, and 8. Obviously, the biggest number here is 8. That's why there is a term called as max pooling. We're going to be picking up all the maximum elements there. And when you apply this filter, right, so basically why you're actually seeing these color coordinates or these color separation is that we are running a filter which is 2 cross 2 across each of these elements to basically give us a one single element out of 4. Now again, as I mentioned, there are a lot of methods which can be performed, such as average pooling and all of that, and max pool being the most popular one in my opinion, which is widely used. So I thought this should be a deserving mention out here. So the second reason of why again we need to use pooling is to ensure we prevent something called as overfitting. Well, basically, if you do not know what overfitting actually means, so basically it's the concept where your model is so dependent on your data that it'll basically keep on learning through in a very complex way, where eventually your efficiency keeps coming down because it's so data dependent, and pretty much it is there is only limited data that it can work with. By reiterating it gets more complex and more complex, and this creates a lot of error in your data rather than something useful. So this basically will create a lot of inefficiencies, and this will basically give you a big hit on your accuracy of detection. So this is one of the reasons why we go on to use pooling as well. Pooling is done to make sure that there is no overfitting, your model is not seeing something very complex, and as you can see on the screen, we are simplifying a 4x4 matrix into a 2x2 matrix by running a filter. Guys, again, do not get confused. A 2x2 filter is being run on the input matrix to give us this output. So this is not the filter that's being used. The filter is the color coded element that I've just split up to show you an example. So as I've mentioned, we're trying to basically go on to remove aspects of it to make it simple. By making it simple, your model does not undergo overfitting. Alright, now to understand all of these processes that we have taken up and looked at, here is an image in a gist. So basically the input is where your computer can figure out something like, hey, this looks like a rough gray texture. This is an ellipse, or, this is something like a reflective texture. This is a wheel. This looks like a rectangle. This looks like a structure of a pipe, whatever it is. So something like this will be the input that you actually provide, and your computer can figure this out. Now, after running the input and the result through a completely configured neural network, your output will be something like this. So since you're working with image categorization, so here's an example. Like, for example, it'll tell you that there is a 1% probability that this image was a cat. A cat will not have a reflective texture. Your cat will not have any ellipses on it, or your cat will not have a rough gray texture all around it. Maybe yes, that's the reason your model has told you that, hey, this is 1% of a cat probably, and then it has given you a guaranteed saying that, hey, this is 99% a car and I'm sure of it. So what would you pick if you had not looked at the image? So basically you will understand that there is a good chance that ellipses are present in the form of wheels. Reflective texture is probably paint. Rough gray texture can be something such as the bumper of the car or whatever it is. Now you understand it as soon as you see the car image. Now this is what your computer will tell you. Your computer is basically telling you this is 1% probability that it's a cat, but then there is a 99% probability that this is a car. And then at the end of the day, the result is this is a car because your computer thinks so, and eventually it is telling you with confidence, with a 99% confidence that this is a car. So guys, going from the input to completely having a fully connected neural network layer and running your inputs across these, performing all the operations, convolution, padding, activation function, there's something called as loss function as well, we'll check that out in the demo, and then following that with the outputs, and then having multiple layers of convolution. So these three things that we checked, right? So basically convolution, having the ReLU layer and the pooling layer, this is one entity. This entity can be the input of the second hidden layer, where again another convolution operation is performed, another ReLU operation is performed to basically bring the data to be linear, and then again another pooling operation is done, and this is the result of the second convolution. From the second convolution, again we can go on to create the third convolution and many other layers as we desire. Again, I'm going to show you all of this and what it looks like with respect to code when we check out the demo. So just before we move on to the demo, we need to understand again and reiterate why we have to make use of CNNs. So why is there that strong need of convolutional neural networks in today's world? So when you're working with image processing, when you're working with image recognition, image classification, convolutional neural networks are the most popular entities there are. There is a reason for this because when you're working with convolutional layers, it will only require a small set of parameters, it will only require a small set of data to basically tell you what it means, and that it can understand a lot with a lot less. I'll repeat that. So your machine can understand what something means by you providing it only a little amount of data. You do not have to provide it a lot of data, a lot of parameters, a lot of features to actually make it understand what the image is. You'll only be giving it a little and eventually the job is done. Well, of course, that's a win-win for you and the system as well. For you because you just gave it a small amount of data. For the computer because the computer could understand it and probably the speed of computation was very high. It was very efficient and all of this, right? Now, so I told you that there will be a smaller set of parameters. Why is that with respect to convolutional neural networks? Well, there's something called as parameter sharing. Parameter sharing is basically, it acts like a feature detector, understanding where the edges are there, where the corners are present and all of that. And then when we come to connection sparsity basically will give you this relationship between the features. It'll tell you, what, I only need this particular feature to give me one single output, or it'll tell you here is a combination of few features which are basically the features which I require to get the output. So considering both parameter sharing and the concept of connection sparsity, we arrive at this conclusion that only small sets of parameters are required when you're working with convolutional neural layers. So this is what that makes convolutional networks as powerful as they are. So to conclude on this, we can go on to say that convolutional neural networks are very popular because they can train really well by making use of smaller data sets, which in turn means that there are less number of parameters in the smaller data sets, and eventually your accuracy of detection can still remain high by making use of CNNs. Guys, this is why CNNs are very popular. I hope I was clear with this again. Now, let us quickly go on and check out our demo where we'll be discussing a small hands-on where I'll be explaining how you can go on to work with convolutional neural networks with respect to Python. So whenever you're working with neural networks, or whenever you begin understanding neural networks, it is extremely vital that you take it slow, keep your learning very structured, and you understand everything from the basics. This is exactly the reason why I have picked up this particular demo for you guys. CIFAR 10 is an amazing data set which basically consists of like 60,000 images each, and this 60,000 images is divided into 10 classes. So there are 6,000 aeroplane images, 6,000 automobile images, 6,000 images of birds, 6,000 of cat, all the way till 6,000 truck. So when you add up all of this, you will get 60,000 images, right? So this is the data set that we'll be using to perform and teach our neural network something. So let me show you what it actually looks like. In fact, this is what it would look like. You can see this is an image of a bird, this is an image of a dog. This is the image of an automobile, a horse, another dog. Again, you can see as another dog. There's a horse here. There are two trucks. There's another bird as well. So since this is a sample of the data set, you might be wondering, hey, why isn't each of these images like a high definition image or an image where, as soon as I look at it, I can figure it out? Well, again, as we spoke about this, when you're training your neural network, this level of pixelation or this level of images, basically this is a 32 cross 32 image size. This is more than enough for your model to accurately predict what it is as well. So in that case, as I told you, giving it small and still getting the result, that's a win, right? So now I hope I am clear with this data set. So this is a very famous data set. It's called as the CIFAR 10 data set, and I would suggest all the beginners or the intermediate developers who are jumping into the world of neural networks to actually go on to work with this data set on your own to get a thorough understanding of how convolutional neural networks works. Now, coming to the actual working of the demo, there are multiple steps here, and let me break down each step for you guys so that you can understand all of this in a very simple way. Coming to the first step is basically importing all of the dependencies that Python requires for you to work with deep learning concepts as well. And the first most important thing is TensorFlow, and we have Keras. So Keras API basically runs on top of TensorFlow, which is a deep learning library provided by Google, and in fact they directly give us the CIFAR 10 dataset as well, and that's the reason we are directly importing CIFAR 10 from the datasets of TensorFlow and Keras. Then we're importing the sequential model, and then we go on to import the sequential model. The sequential model is basically an API which will help us to stack each of these individual layers one after the other. Then we have the convolution 2D layer, the max pooling layer. We'll be flattening the images, and we'll be using dense layers as well. And after that, we'll be importing something called as Adam. Adam is an optimization entity, and we have concepts such as sparse categorical cross entropy loss as well. Again, we're going to talk all about this in the further section. And then lastly, we'll be importing matplotlib. Matplotlib is another beautiful library in Python which is basically used to give you visualizations of your data. So step one, again, I'm making use of if you're wondering what Python Jupyter Notebook this is, I'm making use of the Google Collaboratory, and Google Collaboratory is basically a Jupyter Notebook which is hosted on the Google ecosystem as well. So you can take your code wherever you go with you without having a local dependency of storing it in your PC. It's basically Google code on Google Drive, if I have to explain it in a very simple way. So again, coming back to the demo, let me quickly go on to execute the step one, basically where we're importing all the dependencies as we just discussed, and now that is run. So now that we are done with the first step, which is basically importing all the dependencies, the second step is how we actually go on to set up the model. What does the model look like, what the model has to do, and much more. So basically, upon model configuration, the first entity is something called as the batch size. Once we put batch size as 50, what we actually mean is that so with each iteration of the model working with your data is actually split into 50 samples every single time it is fed forward in your network. And after 50 values have been fed, it gets computed, and there is something called as loss, which is basically computed. Basically what I'm trying to tell you guys is that you can specify how many batches you want your images to be split and sent by making use of batch size. Now coming to image width, image height, and the number of channels. Basically the image width is 32 pixels, the image height is 32 pixels, and the number of channels is 3. Again guys, as we discussed at the start of the session, the number of channels is basically indicating that this is an RGB image. Now coming to the loss function, as I mentioned, so we're basically going to use something called as a sparse categorical cross entropy loss. What the loss function basically is it'll basically so it'll go on to compare a lot of the outputs that it has to check out if the prediction is correct against whatever is true or not. Let me repeat. The loss function is a direct comparison between what the model has predicted versus what exists in real life. As I told you, since this is a labeled data set, we'll be providing a dog's image alongside that it is a dog, and we're actually asking the model to tell us how it thinks that it's a dog. Right now, when we do something like that, there is 100% probability that the image is a dog because it knows it's a dog. Now model may have predicted saying, hey, you know what, I only think that this is 70% of a dog. Now the loss there is 30%, right? So that is a very, very, vague, simple example of what a loss function would seem like. Of course, we can go on to get into depths of understanding a lot of loss functions there are, and how it works as well. Because so whenever you're working with integer elements or any data in the categorical format, there are multiple ways you can change and work with these data as well. Now anyway, to keep this demo again simple, let me quickly jump back to the next line of code, which is basically the number of classes. With respect to the number of classes, or let's say even the number of epochs of the next sentence in the code, what we're trying to set here is that once we've set the number of classes to 10 and the number of epochs to 20, we're trying to say that every time, so basically we're trying to tell the neural network model that you can have 10 classes of data movements, and you can perform this operation across your neural network model 20 times to learn. The number of epochs again can be changed, the number of classes can be changed, and the number of epochs can be somewhere like 100, it can be 200. This is not set, because again with every epoch your model is training completely on the data once. Now if the number of epochs here is 20, it means that the model is training 20 times. And you might be wondering, okay, if we make the model learn 10 times, I might get a 90% accuracy. If I make the model work a million times, what about it? Well, not really. If you're making your model work a million times having a lot of epochs, what you're trying to do is you're trying to overfit the model again. Again, as I mentioned, your model will be seeing a lot of data with every single iteration that it will get confused thoroughly. Again, guys, we're going to see what overfitting actually means visually at the end of this. So make sure you stick till the end as well. Now, coming to the optimizer, again, the optimizer is the concept where we are updating weights, the concept of weights in the neural network. So why we actually go on to use something called as the Adam optimizer is that Adam optimizer is one of the most widely used, one of the most commonly used optimizer when you're working with a neural network. So basically, when you're working with a neural network, loss functions are something important that you have to understand, and optimizers are something that you have to understand. So with respect to optimizers, when we talk about it in a simple way, these are nothing but simple methodologies. These are nothing but algorithms. These algorithms will change concepts in your model. In this case, in an optimizer, what we are trying to change is something called as the weights and basically learning rate as well. So when you do this, this will ensure that your model understands that it's learning. So every time it sees a lower number in the loss, it understands that I'm getting closer to learning this accurately. So basically, to do all of that, again, in the process of backpropagation, in the process of feeding forward your data, we're going to use the Adam optimizer to basically go on to achieve just this. So now you might be wondering, what the next set means. What is validation split and what verbosity means? Well, guys, validation split is basically us telling that, hey, let us make use of 20% of our training data, which we later put it into validation. So 80% of the data that we give it will be used to train, and 20% of it is stored separately where your computer never sees these 20% images, and these 20% of the images are actually used to test if your model has learned something or not. Now think about it like an examination. So let's consider the concept of an examination. Let's say there are 15 questions in your class, and then with 15 questions you only know 10. And when you appear for the examinations, you have these other 5 questions which are shown there as well. So now if you already knew all 15, there is no point of it, because you would have learned all of this. There is no way to verify. Now if these 5 questions there were not known to you, then you can actually use that to validate if you have actually learned something. Again, this was a vague example to basically to tell you why we need to split the testing data and the training data as well. So again, to reiterate, our data is being split where 80% of the data is used to train, 20% is used to check if it's learned or not. Now coming to the verbosity part of it, verbosity, which is 1 or it's actually binary, it's true. So with respect to what this is it'll tell us in a textual way by showing us the output, how your model actually learns. So when you work notebook or anything else, you can actually hide all the elongated and huge outputs that you get. But then if we put verbosity equal to 1, we can actually see what goes on when your model is learning. And to show you guys that, we've gone to use verbosity 1 as well. Now, after all of this, we need to import our CIFAR10 data set, and we need to, go on to make the model understand what data we've pretty much inputted as well, right? So now that we've discussed about the CIFAR10 data set, all we're trying to do with this particular step is to load it and help our model understand. Again, the CIFAR10 data set is provided by the Keras API and the TensorFlow people directly as well. As I told you, it's a very popular data set, and in this particular case, it's actually downloading it from its source. Its source is basically cs.toronto.edu, the website you can see there. And so it's gone to basically load the data set, and after that there is one simple step that we need to do. Now, so whenever you're working with the Keras API, it needs to understand what your input will look like. So basically you have to determine the shape of your data, and you have to store it in a variable where you're telling Keras, you know what, hey, this is what the input layer can be look like. Because if we provide it with what the input layer looks like, it can go on to compute the hidden layers and eventually give us the output as well. So what we're trying to tell Keras is that this is basically the input image width, this is the height, and these are the number of channels. Now, after we have done that, step 5 is something interesting, because step 5 is basically converting all of the data that we have sent the images. Again, image width, height, and channels, all of these can be integer numbers, right? 32, 32, and 3. To be very precise. Now, we're going to convert all of this into a different data type, and this data type is basically float 32. So why we are doing this? Again, basically, it actually speeds up the operation a little when we convert it to float. And then after converting all the data types to float, we do the normalization operation. Normalization basically, so your data can be a lot of different numbers in matrices that we discussed. By doing the normalization operation, all we're trying to do is, we're bringing the data down to a range in between -1 and +1. As you can see, all we're trying to do is we're actually taking the training set and the testing set, and we're dividing it by 255. And this gives us the number range basically from -1 all the way to +1. And after that, step 6 is a very important aspect of it. I'll tell you why. Step 6 is where we actually go on to create what the model looks like. As I told you, we'll be using something called as a sequential API. Sequential API, if I have to explain it, think of it like it's the foundation of how your model will work. Whenever you're basically doing something like a puzzle, whenever you were kids, you were working on puzzles. So the two pieces that will fit together, the part of it which fits into one, which the part of it where one piece fits into the other, right? So that can be directly relatable to how the sequential API works in our particular model as well. So basically, we are trying to create layers by making use of the sequential architecture, one layer after the other. So a neural network will have one input layer, multiple hidden layers, and one output layer. So by using this, we can go on to create multiple layers. In our case, how many layers do we have here? So as you can see, we have actually made use of multiple layers here by making use of the sequential API. And if you're looking at the aspect of, hey, what's changing out here? If you're wondering what the kernel size means, kernel size is basically the same as filter size, guys. So filter is also called as the kernel. Now, if you're wondering at why there are numbers such as 32, 64, or 128, these are basically the number of feature maps that will be running in that particular layer of the neural network. So after understanding that hey, our first layer will have 32 feature maps, our second layer will have 64 feature maps, the third layer will have 128 feature maps, and much more. And we are making use of max pooling. I explained what max pooling is. Basically, after running the filter, we only pick up the maximum element on that particular cross section of the filter and the input. So max pooling 2D is done to do directly that. And after this, we'll have a generic pattern of how the model works. This is done in a repeated fashion to go on to understand and make your model more efficient as it trains. So after all the convolution operations are performed, we have something called as flatten. Well, what does flatten do? Well, to explain it in a very simple way, this basically, all the dense layers are the ones which are responsible to make your classification. Those are the layers which will say, hey, this is a cat, hey, this is a dog, hey, this is an aeroplane. And this flatten layer, so basically this flatten layer ensures that this will happen. It'll make sure that it is actually generating a sort of classification operation there. So after all of that is done, we convert it into one output layer, and that is basically what we're doing after this as well. As you can see, we discussed the activation function to be relu, which is rectified linear unit. In fact, as I told you, there are multiple other activation functions as well. Softmax is another very good activation function too. And now at this point of time, we have created the model, and we have told the model what it's supposed to do, how many layer it's supposed to have, what sort of pooling operation it has to do, how many convolution layers it has to have, what is the filter size that it needs to see, and performing operations such as flattening and dense operations to make sure that we get one single output layer at the end as well. So you might be wondering, why is it that we made use of softmax at the end, right? Well, softmax is basically used to give you a discrete probability distribution for your output. This will basically tell you that what is the highest probability that your image is a cat, what is the highest probability that your image is an aeroplane, or is it a horse, or whatever. So to get this discrete output, we make use of the softmax activation. Now, coming to step 7. Step 7 is the most important aspect, because this is where your model is compiled. This is where your model will learn based on accuracy, and this is where your model will know what to do. If you can see from the compilation, we have given it the loss function as we have previously discussed. We have given it the optimizer as well, and we're training it on the basis of accuracy. So after the compilation of the model, this is in fact a very skeleton looking neural network, if I have to tell you, because we have set everything up previously when we have pretty much set up the model here in step number 2 as well. Step number 7 would have been really big if we had to do everything here, and again, I didn't want to overwhelm you guys, and that's the reason why we have split it up as well. So when you're working, so this is the step which will take a lot of time when you're compiling the model, because here is where your model actually learns. Here is where your convolutions, your poolings, all of this will happen multiple times, and your training data is run across every single time, and worked with it as well. So this is going to take a couple of minutes, and again, don't worry, we'll just try to see if we can speed up the video a little here as well. So when you're wondering about what's happening here, is that with every epoch, you can see that the loss is actually coming down. It means that your model is understanding it. See, as of now, how much ever images it has seen, it can only tell you a maximum of 28% accuracy that it's correct or it's wrong, or that it's classifying the images right or wrong. Now, as soon as the epoch starts to complete, or if one epoch starts to end, you can see that the loss keeps coming down and the accuracy keeps going up. So with more and more epochs like this, with more and more iterations of your model running on the training data, we can make sure that the loss is minimum and the accuracy is high. So as I mentioned, this is going to take some time, so let it complete and I'll just be back. So guys, as you can see on your screen, it's finally done. It took quite amount of time, but the most important thing that you have to understand here is that the loss came to be very low. We started with every iteration, basically you can see that the loss went from 1.6 all the way till 0.1, and the accuracy of detection went from zero point 0.3 all the way to 0.93. So this is a percentage, 39% of accurate detection all the way till 93 percent of detection. So ladies and gentlemen, this is the most important thing we have to understand about step number 7, because here is where your model actually trained, your losses came down and your accuracy went up. So on that note, to actually understand your model evaluation, we have to go on to plot a couple of curves. So here is where we'll be using matplotlib to basically plot what the loss looks like, what the accuracy looks like, and we'll generate our test score as well. So with respect to validation loss, you can see that the loss kept on coming down as soon as we kept training it. So on the x-axis we have the number of epochs, on the y-axis we have the loss values. So as you can see, with respect to multiple epochs, our value kept coming down, and after somewhere around 8 epochs, you can see that the loss was actually, validation loss was increasing. So why this basically happens is, again, as we discussed, overfitting happens where your model will be delving so deeper and deeper into your data that it'll actually get confused with a lot of noise. It'll get confused with all these deviation, that it moves away from accuracy. This is the reason why you can see that to the 8th epoch, basically your validation loss rises up again. But then coming to the accuracy value, you can see we hit maximum accuracy somewhere around the 12th epoch or somewhere around the 8th epoch as well. So whatever curve is higher up here, I think it's the 8th epoch. So here is where we hit the maximum accuracy of detection basically. And after that, it has been dwindling around basically around somewhere around 67 or somewhere around 70% and above that. Again, this is because of overfitting as well. So this is why it becomes so extremely vital to remove overfitting whenever you're working with model. And of course, at the end of it, we have almost 70% accuracy when detecting what an image is. There is 70% probability of an image being an aeroplane, or it being a cat, it being a horse, and whatnot. And this is something which is very important in the field of neural networks, ladies and gentlemen, just as I mentioned. And I hope I was very clear with this demo as well. Anyway, coming on to the final sections of it. So as you guys always ask us about the average salaries of these particular technologies we work on, I thought it was fitting enough to show you the average salary of an artificial intelligence developer. So the average salary of an AI developer in the USA is somewhere around $150,000 per year. In India, it's somewhere around 19 lakhs per annum, and in the United Kingdom, it's somewhere around 81,000 pounds as well. So with these numbers on your screen, you can figure out that this is a very lucrative job, and having a career in artificial intelligence not only pays really well, but it is so much fun to work with at the same time. This brings me to the final thoughts. So basically, my final thoughts, it's always a quote, and this particular quote is amazing. It's by a person called as Brian Kernighan, and he says, "Controlling complexity is the essence of computer programming." So as you just saw, something as simple as an image processing system for us human beings can be pretty much, not complex in the neural network terms, but it can be certain, of course it can be certain level of complex when we are actually checking it out and making the computer learn as well. So controlling that complexity is basically everything which involves computer programming, and this quote is really well. So make sure you jump on this trend. Artificial intelligence has been on the rise ever since its inception, especially in the 21st century. It is gaining nothing but traction. It is showing nothing but a lot of future scope. So make sure you jump on the artificial intelligence train and make the most use of it. So coming to the further learning section, basically this section involves other favorite quote of mine. It says, "An investment in knowledge always pays the best interest." Ladies and gentlemen, this is a very strong quote. This is by Benjamin Franklin. And so basically you might have questions saying, okay, where do I check out neural networks in depth, or where do I check out any concept of IT related stuff in detail? Well, ladies and gentlemen, we have a comprehensively put together YouTube channel where you have access to all of the content that we upload. So make sure you check out the YouTube channel, make sure you subscribe, make sure you hit the bell icon so that you never miss updates from us. And if you're more of a blog reading person, we have an entirely dedicated blog channel where we have software architects, we have experts, we have researchers who write a lot of blogs for you guys to read as well. So make sure you check out Intellipaat blogs too. And then coming to the community, we have Intellipaat community where it's a very friendly community where people across the world come indulge and delve into the world of IT, and pretty much one person can ask a question regarding any of the concepts of IT. We cover a lot in the Intellipaat community, and a lot of others come help the person out by answering it. It might be something like a basic query all the way till some complex code structure where the person is stuck or needs some help debugging everything. So make sure you check out Intellipaat community as well. And on that note, let me quickly come to the part where I told you I would guide you on the fastest way you can become experts in artificial intelligence. I present to you Intellipaat's artificial intelligence course and training. Basically, this is done using TensorFlow. This is one of the top programs here at Intellipaat, which will basically help you master everything with respect to neural networks, even recurrent neural networks, convolutional neural networks, the concept of perceptron, TensorFlow, GPU libraries, Keras, again, as I told you, Keras, TFLow, APIs, backpropagation, hyperparameter tuning, and much more. Coming to the key features of the course, we have 32 hours of instructor-led live training. So this basically takes place in a virtual classroom online where the instructor is teaching you guys live. If you have any queries, you can of course pause the session and ask the instructor and clear it then and there. We do have 24 hours of self-paced videos, and we give you 48 hours of exercise and project work as well. So here at Intellipaat, we believe you require all the project work and all the exercise, because at the end of the day, this is what is going to count as validation for your knowledge, and of course, this is what is going to count as a very foundational step, pretty much when you go on to work on projects or when you get hired as well. And certification and job assistance alongside flexible scheduling and lifetime free upgrades are some of the most major highlights we provide here at Intellipaat. And of course, we do give 24/7 lifetime support, lifetime access to all of the courses as well. So ladies and gentlemen, quickly coming to the artificial intelligence course content, there are multiple modules here. You'll be starting with introduction to deep learning and neural networks. You'll be working with multi-layered neural networks, just like how we worked on artificial neural networks. What are the various methodologies? There's something called as lasso ridging. There is unsupervised training. There's Xavier initializations and much more. And then we have the deep learning libraries, various deep learning libraries on how you can go on to work with TensorFlow as well. There's something called TPU, Tensor Processing Unit. You'll be taught about all of that. You'll be using the TFLow API for TensorFlow, deep neural networks, convolution neural networks, recurring neural networks, and much more. All the way till application of deep learning, chatbots, time series. Ladies and gentlemen, as you might have figured out, I can go on and on with respect to the curriculum. In fact, to download the curriculum in detail, make sure you hit the download curriculum button as shown on your screen, and you can get this curriculum and you can take a detailed look at it as well. And after this, we have all the projects, industry level projects we provide for this particular artificial intelligence course. And as you can see, we provide 3 industry level, industry grade projects that you'll be working on after learning all the concepts in this particular course. And this is something important, because here you can see all the projects you'll be working on, the industry with respect to the project, what is the problem statement of the project, a little bit of description about the project, and eventually all the highlights of what you'll be working on as well. We do provide sample videos too, so make sure you click on this particular play button to access the sample videos of this course. And upon course completion, you will be awarded a certificate which looks just like this. This certificate is very well recognized in companies like Ericsson, Cisco, Cognizant, Sony, Neosigma, Saint-Gobain, TCS, Genpact, Hexaware, and much more, ladies and gentlemen. And if you keep scrolling down, you will see all of the detailed reviews, feedback, and all of the content, and whatever our learners have to say about us as well. So make sure you check out all the feedback too. And the last section involves the frequently asked questions, and we're sure you'll have a lot of questions about the course as well. And just before I answer more questions that you might have, let me quickly give you this particular offer. So here at Intellipaat, we believe that you should make complete use of this situation. So we are providing you a 30% off to all of the viewers who stick till the end of this video. So make sure you use the coupon code YouTube30, YOUTUBE in caps, 30 in numeric, to get flat 30% off on all of the courses we sell here at Intellipaat. Artificial intelligence is on the trend. Pretty much, at this point of time, we're all safe in quarantine. Let's make sure to keep our learning up. This is the start of a fresh decade, and to make maximum use of it, this is Intellipaat's help to all of you guys. So on that note, you have reached the end of the session. If you have any comments, any suggestions, any content requirement, or anything of that sort, again, head to the comment section and do let us know now. If you're confused about what course that you have to pick up, or if the course is right for you, or much more, we do have our course advisor standing by 24 hours of the day, 7 days of the week, and 365 days of the year, waiting to help you, dear learners, out. So make sure you give us a call on the numbers mentioned on your screen. I have the Indian numbers and the US numbers on the screen. So if you're more of an email person more than a calling person, of course you can leave us a mail, sales@intellipaat.com, and we'll be more than happy to help you out at the earliest. On that note, I wish you took away a lot from this session, and make sure to keep your learning up and stay safe. Alright, I'll see you on the next one. Goodbye.